Okay, question 3 of the sample material physics paper 1 higher tier for Edexcel GCSE 9 to 1. 3a, figure 2 shows some lines in the absorption spectra from 4 different galaxies, A, B, C and D, and from a laboratory source. All of the spectra are aligned and to the same scale. Explain using figure 2 which galaxy is furthest away from us. So we can see that this pattern of black lines is repeated on all of these different spectra, but at different points. Now the lab source is what it would be like in a lab, and then we can see that it's been shifted along. And the one it's been shifted along most for is C. So C is furthest away from us. Now why is that? And it's because it has the greatest redshift. Redshift is that as a galaxy moves away from us, the light from it is stretched and the wavelength is increased. And you can see here that the wavelength is going this way. So the wavelength of this light is longer than the wavelength of this light. These absorption lines are at different points. This is at a longer length. So C is furthest away because it has the greatest redshift. Now that can't be 3 marks. If it has the greatest redshift, it therefore has the greatest speed. Because it's the faster you're moving, the more redshift you have, therefore has the greatest speed. And so is furthest away. Now why is that? Because Hubble's law tells us that recession speed, as we call it, moving away from us speed, is proportional to distance. So the further away you are from us, the faster that galaxy will travel and the greater its redshift will be. That is Hubble's law. That is what Edwin Hubble determined when he found out the universe was expanding. Question 3, part 2. In figure 2, the reference wavelength lambda naught is shown at 390 nanometers. That's this here, so lambda naught is 390. Estimate the change in the reference wavelength delta lambda, that's change in wavelength, for the light from galaxy D. If I look at D, if I draw a line here, using a ruler normally, it's at this point, and we've got 1, 2, 3 scale divisions between 390 and 450. So each of these scale divisions must be 20, and this must be 410, and this must be 430. So the change in wavelength there, delta lambda, equals 20 nanometers, because this scale, as you can see, is in nanometers. And then it's going to ask us to calculate the speed v of galaxy D using an equation that you haven't seen before. This is a redshift equation. You wouldn't see this until year 13 of A-level if you do Edexcel for A-level. And they've given you that C is the speed of light, which is 3 times 10 to the 8 meters per second. So we're just going to sub the numbers in. So V equals C, 3 times 10 to the 8, times by the change in wavelength, which is 20, divided by the reference wavelength, which is 390. Now these are in nanometers, and I could, if I wanted to, convert them into nanometers, but because they're both in nanometers, it's not a massive issue because they'll cancel each other out. So I'm just looking for my calculator, which is nowhere obvious. Oh, here it is. I'm going to show you how I put this into the calculator. So to do this sum, I'm going to write 3, and then there should be a times 10 to the button or an X button somewhere, 8. I'm going to do equals, that's my number, 3 times 10 to the 8, times by 20, divided by 390, and it comes out as this lovely long number, which I'm not going to write out. I'm going to write it as rounded, and to help me, I'm going to press the eng button, because the eng button puts it into a not completely standard form, but into a times 10 to the value, which is really useful. So I'm going to write this as 15. I'm going to round that, 4 times 10 to the 6 meters per second, which is the answer I put in there. It's a really useful button, the ENG, I think it stands for engineering button. Okay, part B, figure 3 shows a photograph of galaxy D. This photograph was taken by a student at his home. State 2 ways that the student can improve the observational technique so the quality of the image is improved. So if they want a better and clearer image, what can they do? Well, firstly, they can use a better telescope, but you can't just say better telescope, you have to say how you'd make that telescope better. A bigger aperture or lens, that's a large diameter, would mean that more light is collected, which is going to give you a clearer image. Or they could move to better conditions. So they could either move higher up in the atmosphere, because if you move higher up in the atmosphere, you're reducing your atmospheric distortion. As light comes through the atmosphere, it's kind of twisted and bent, and this is why stars twinkle. Stars don't actually twinkle. I know that's quite sad, but there we are. What actually happens is that as the light comes through the atmosphere, it makes the stars look like they're twinkling. So if we can get higher up in the atmosphere, that happens less. Or we could move to a darker area, as this would reduce light pollution. So if he was in a city, if he went to the countryside instead, if it's darker, then he's going to get a better image with more contrast. So that's question 3.